Greetings. So we're going to continue our discussion with energy, just to get a better understanding what energy is, etc. And interesting, like it's really interesting. Like energy, um, actually is really helpful to think of physical systems in terms of its energy. It just makes things so much simpler. And even some of the kinematic equations, how you would have solved them based on just kinematic equations, can be very tedious. Whereas if you just consider them in terms of energy, they become so much simpler. Um, so we want to get an understanding of specifically mechanical energy, right? So not chemical, not maybe the energy due to the electrons, etc. We want to think about just mechanical energy. So according to physics, energy is neither created nor destroyed. And again, there's different types of energy, such as kinetic, potential, rotational, chemical, and so forth. But we will stick with two of the mechanical ones, which are kinetic and potential. And I will discuss what these are and how to use them, etc., where they come from. But another thing is too that if you have an isolated system, right? Say you have a box and then you have this like physics system, right? Say you have a galaxy here. And it's not affected by other like outside forces, right? By anything from the outside, right? This galaxy is on its own, far, far away from other things. So the energy of this galaxy, according to physics, will always stay the same. Now, things might happen in here, might things might change, but the total energy is not going to change. And what do I mean by that is that, for example, in some parts of the galaxy there could be balls, or there could be balls on cliffs, right? And then a ball on a cliff actually has stored potential energy because it has the potential to fall and turn that into kinetic energy. Now, if this is unclear what potential and kinetic energy is, don't worry, I'll explain that about it. But in essence, what I want to say is that energy is in different forms: kinetic, potential, chemical, rotational, etc. And it can also transform into other types of energy. Maybe as a brief example, like our sun, right? It has all these photons that hit Earth, right? This is my bad drawing about Earth. And it heats up our environment, allows us to do photosynthesis, etc. So this energy that comes from the sun is then given to the plants, which then we as humans eat to give us energy, right? So and then we have stored chemical energy such as glucose, etc., that we use for then running, right? Uh, we use to running or just to do our daily activities, and so forth, right? So a lot of the energy that we have in on Earth is given by the sun, right? Which is actually like really cool, right? From a natural and spiritual point of view. But anyhow, um, so going back, kinetic energy can transform into potential energy, and potential energy can transform into kinetic energy. So at different times, our system might have maybe more kinetic energy and less kinetic energy and less potential energy. Um, and then sometimes it might have less kinetic energy and more potential energy. But the total amount of energy in the system will not change. So there's two different types of mechanical energy: kinetic energy, um, and kinetic energy is energy from movement, right? And the equation that we use is 1/2 meters per second times velocity squared. Okay, so we have our mass times our velocity squared. This is mass, not meters. Excuse me, and this is velocity squared. So moving object's kinetic energy depends on its mass and its velocity. Its units are joules, right? J. And so we have kilograms mass squared, and so we have kilograms times meter squared divided by second squared. Excuse me, and that that set of units there we abbreviate with the letter J, which are the units of energy, joules. Now, a moving object, say a car, can transfer its kinetic energy to another object. Say if it crashes, right? So, a moving object, say a car, can transfer its kinetic energy to another object. This transfer of kinetic energy is called work. So, imagine you're like in a car, right? And then you hit another car. It's terrible, terrible accident. But what happens is that if for example you were like in an icy road and you didn't really care about maybe the noise or the heat generated by this collision, then some of the kinetic energy from car 1 will be transferred to car 2, right? It will push it, so then this car, which could have been at rest, right, zero velocity, would start moving with a velocity maybe at 50 miles per hour, or maybe 20 miles per hour to be more reasonable. So then this object, this car, gains kinetic energy. So we're transferring kinetic energy from one object to another. Kind of like billiard balls, right? So if you have like a game of billiard and you hit one, and then you hit another ball, like, I don't know if you've seen it, but like sometimes the first ball stands still and the second ball starts moving. And so then like kinetic energy is transferred from one ball to another ball, and then etc. You play the game until you finish it, right? But so this is a really interesting topic, right? Where like we're able to transfer kinetic energies from one object to other objects. So this is basically transfer of energy. And that leads us to a nice theorem called the work energy theorem. Now, again, if you haven't heard about this, it's totally fine. We will talk about what work is, if you haven't heard about that either. But basically what it says is that the change in kinetic energy is equivalent to work. Okay? And that's what we have here. Change in kinetic energy is the same thing as work. Okay. Now, work can be positive or negative. So, for example, in this case, car 1 is changing cars 2 kinetic energy, right? Maybe its kinetic energy was 0, and then its kinetic energy was, 10 joules, right? So car 1 is doing work on car 2. But also car 2 is doing work on car 1. It's just negative work, right? Because it's taking away energy. So the change in kinetic energy in car 2 is positive, whereas the change in kinetic energy in car 1 is negative. So that is where the negative and positive work comes from. They're changing kinetic energy. Okay? So let's go over a brief description of what work is. Work is force times distance. That is the definition of work. Force times distance. And it's easier if you have a constant force over a distance, right? So, for example, you have a block of ice over an ice sheet, right? All level, etc. And now you apply a certain force on this block of ice, right? Over a certain distance d. Now it goes from a velocity of 0, say if it starts at rest, to a velocity of 10 meters per second squared. So after applying this force over a specific distance, you have increased this object's kinetic energy. Now that's pretty cool, right? So there is a there's a change in kinetic energy, right? Your kinetic energy at the beginning, because velocity was 0, your kinetic energy is 0. And then, because your velocity now is 10, your kinetic energy will be equal to 1/2 of your mass times your velocity squared, which is 10, right? Okay? So, it is true that the change in kinetic energy is related to work, right? Which is force times distance. Okay? So, that's cool. Maybe let's just look at the units. So we have force, which is mass and acceleration, right? And then we have distance. So now mass, the units of mass is kilograms, the units of acceleration is meters per second squared, and the units of distance is meters, right? So then we multiply these two together, and that gives us was meters squared over seconds squared. Okay, so we have kilogram times meter squared times second squared. Now from Newton's first law, okay, so, and this has to do with, in some way, in Newton's first law, like, if we don't apply a force, an external force on an object, it won't stop moving, and it won't start moving, meaning that we need an external influence to be able to move an object. It won't stop moving or start moving on its own, unless it has some sort of, well, like this block of ice won't stop or start itself by its own, right? Okay. And how does this relate to maybe the car? So the car here is moving at a certain velocity of, I don't know, 50 miles per hour. And then it hits this better semi, right? Now, when it hits the semi, when it crashes into it, right? It actually will apply a force on this other semi, right? There'll be a force that is applied on this semi, and it'll push it for a certain distance. Howbeit, this force might change over this distance, right? So this force might not be constant. Okay? And you can calculate. You can also calculate that using calculus, etc. More like complicated things. So your force can change over the period of distance, and we can still calculate work. So the theorem still holds. The theorem still holds. It's just that we need to use more complicated math to be able to describe it, right? Okay. Okay. So now we can actually figure out where this kinetic energy comes from. Like, say for example, we have no idea where it comes from, etc. And how to calculate it. Then we can just use our definition of work, right? Changing kinetic energy equals work, which is mass times acceleration times distance. And that equals mass times acceleration times the change in displacement, or distance in this case. Okay? Now we can use our kinematic equations, which gives us this equation. It's a very nice equation, right? And we can solve for A times change in displacement, right? We can move this to the other side, divide by 2, and that gives us this equation right here, okay? And now we can plug it in back to our initial equation that we had here. So change in kinetic energy equals mass and acceleration times the change in displacement, right? So this m times change in displacement becomes this equation, okay? And this is where we get 1/2 mv squared, right? Now, assume that your initial velocity is 0. Then what we're left with is that my kinetic energy now is 1/2 meters per second squared. This would be like your final velocity. Okay? And you can see this is what our equation was before, right? It's really nice. Yeah, so this is where it comes from. Okay. Now I have left a few calculations, and I will share this PDF so you can maybe go over it, but I'll just scroll through it. And so this is just an example of how we can calculate, for example, kinetic energy. Let's go to potential energy. So potential energy, you can think about it as stored energy, right? Stored energy in an object due to its position, properties, or forces acting upon it. Now, potential energy can come from different ways, right? From gravitational, elastic, magnetic, electric, etc. But since we're only focusing on mechanical energy, we're just focused on gravitational. Potential energy comes from gravitation, right? Now, you might also be looking to elastic potential energy later on in your course. due to like say springs and coils and stuff like that, which is pretty cool. Um, so these have the potential to transform this energy into kinetic energy. Okay. So potential energy, for example, if I have a ball, and then the earth shakes for a minute, and then so this ball is pushed off and starts falling. So this potential energy that it had changes into kinetic energy. Okay. So again, we're gonna go back to our ball example, and we're actually gonna maybe try and figure out where does how does P potential energy for gravity look like, and like is equation, well, I'm gonna spoil it, is gonna be mass times gravity times the height in which it falls, right? So this height will be in this case 10 meters, right? Okay. And what we're going to use is this definition of energy, where energy is neither created nor destroyed, and our total energy, say for example, so let's call this 1. So the energy at 1 is the same as the energy, let's say at 2. Energy at 2. 2 is right before the ball hits the ground, okay? So energy at 1 will be your kinetic energy at 1 plus your potential energy at 1. And energy 2 will be your kinetic energy at 2 plus your potential energy at 2. Okay? And these are the same, right? Your kinetic energy might change in position 1 to be greater or smaller, and then also your potential energy might change. But the sum of these two would equal each other. Okay? And that is what we're going to use. Okay? So this is have 1 and 2. 1 and 2, right? So in scenario 1, the ball is at rest. Your velocity is 0, so there's no kinetic energy, right? No kinetic energy because kinetic energy relates with velocity squared. So the velocity here is squared is 0, therefore kinetic energy goes. So what we're left is only with potential energy, okay? Now, on scenario 2, the ball falls, the ball drops down, and you see there's almost no height. We're going to measure it, position 2 is just before it hits the ground, right? And so there's basically no height, so potential energy will be 0 in this case, okay? And kinetic energy will actually the ball would have kinetic energy because it starts falling, so it starts gaining speed, as we discussed before. So the object is moving at a certain velocity called v, right? And so now, given that the energy in my system is neither created nor destroyed, my system has the same energy in scenario 1 than in scenario 2. So this means that my potential energy at 1 is the same thing as my kinetic energy at 2. Which is wild, right? Right, because kinetic energy at 1 is 0 and potential energy at 1 is 0. So we don't consider these, right? So we just consider potential energy at 1 and kinetic energy at 2. So we have that PE at 1 equals kinetic energy at 2. Now, we can find what PE is, potential energy is, using kinematic equations, right? Right, we can find what the velocity should be after a 10-meter drop using our kinematic equations, but that's kind of boring. What we're going to do is also use the work energy theorem. And so we're going to use the work energy theorem. So the force due to gravity over a distance d. So again, before Einstein came up with this theory of relativity, we considered the pull due to gravity to be a force, right? And so this ball, which is falling for 10 meters, is actually experiencing, well, according to physics at the time, is experiencing a force, right? A constant force of its mass times gravity over a distance of 10 meters. So my work would be equal to the mass times the gravity times the height, right? Over the distance, right? This is my distance d, my height. And this is my force. Now, so we have our equation for work. Now, the change in kinetic energy, right? is equal to my work, right? So my K final minus K initial is the same thing as work, which equals m times g times h, right? Now, kinetic energy, initial kinetic energy is 0. So our final kinetic energy is equal to m times g times h, correct? Okay. And yeah, so that's what we have. Potential energy equals mass times gravity times height. Okay? I hope that was clear. Again, these topics are a bit confusing and a bit hard. But that's the equation that we have. And again, these are the calculations, like a brief example. If we're given like a 10-kilogram ball falling off the cliff, etc. So I will share this so you can go over it. Now, the last thing that we have to do is power, right? So the power is the amount of energy transferred or converted per unit time. One way to measure its transfer of energy is to measure the change in kinetic energy over time. So we have, so one way to calculate power would be seeing what change in kinetic energy is over a period, right? Or a length of time, right? And again, like kinetic energy is the same thing as work. Changing kinetic energy is the same as work. And work is force times distance, change in distance. And you know that change in distance over change in time is actually velocity. So power can be written as force times velocity, which is my mass, A times velocity, V. And again, its units here will be joules over seconds. And last but not least, I have the sample questions that you showed. Joules is the unit of work. Potential energy is the energy associated with the position and height of an object. That's what we discussed before. If an object has kinetic energy, it is capable of doing work. Work requires force times distance. Joule is a unit for kinetic and potential energies. Kinetic energy is the energy associated with the motion of an object. A watt are the units for power. That's what we had here, right? Joules per second. W is an abbreviation of joules per second. Yeah, and the law of conservation of energy. What is the law of conservation of energy? We discussed about this, like total energy of a system is neither created nor destroyed. Energy is transferred. We're at some, at some point there's more kinetic energy than potential energy, and at other times there might be more potential energy than kinetic energy. So this is my conservation of energy. 1 here represents some time 1, and T2 represents some time 2. Okay? When an object is below the surface, the object's potential energy is said to be negative. Okay, and that is the end of this brief talk about basic physics. I hope you enjoyed it. Please, if you have any questions or anything that you would like me to talk further, just send me a message. Thank you.